Topic 4A. This lecture will introduce root finding methods, talk about some generic things, and then also cover the bracketing methods. In the next lecture, we'll talk about something called the open methods. So as I mentioned, this lecture will introduce root finding methods in general. We will cover two different forms of bracketing methods, although what you'll see, these are extremely similar. And then we'll talk about how to generalize these to handle multiple roots. And that's when we have two roots at the same time, or three roots or four roots, and we can look at the behavior of the function around that root to figure out whether that's single, double, triple, quadruple, or whatever. First, what is root finding? In this case, we have some function f of x. We want to know what values of x force that function to be 0. This can happen multiple times, in which case we have multiple roots. For example, maybe we have this quadratic polynomial. Where does that equal 0? In this case, that's pretty easy to find. We have the quadratic formula to do that for us. And we also know that there will be two roots in this case. But what if we do not have, or we can't obtain an analytical solution? This example, exponent of x, or exp of x minus x, that does not have an analytical solution. We can't solve that for x equals 0. It could also be that the function f of x is a simulation, and there is no equation behind it. It's a whole bunch of procedures and algorithms that eventually spit out an answer. What do we do then? And that's really the purpose of the root finding algorithms, to find those roots in the absence of having some kind of analytical solution. There are roughly 3 categories of root finding methods. In this lecture, we'll discuss the bracketing methods. And in that case, we have to be able to somehow roughly identify where the root is, and then identify some value of x above and below where that root could be. We maybe know roughly that our root is at a value of 2, for example. So we might choose upper and lower limits of 1 and 3. And we want to ensure that those limits surround a root. And then the bracketing method essentially works by slowly adjusting those bounds inward until it closes in onto where the root is. Open methods work differently. They don't have the upper and lower bounds. They have just an initial guess. And it's an iterative algorithm that successively improves on that until that guess closes in on exactly where the root is. A third method, and one that we won't talk about now simply because this also involves curve fitting, which is a topic for later on, but we could take 2 or 3 points in the vicinity of our root, fit that to a polynomial or some sort of function, and then analytically find the 0 crossing from that function. This also comes up. Instead of finding roots, what if we want to find values of x where the function doesn't equal 0, but where the function equals some value of a? And it turns out this is a real simple hack that we can do to our root finding algorithms to generalize it in this way. So we want to find where the function f of x equals a. Let's take a and move it over to the left-hand side of the equation. We now have f of x minus a equals 0. Let's define an auxiliary function g of x that equals f of x minus a. Really what we need to do is perform root finding, our standard root finding, on g of x. So where g of x goes to 0 is where f of x equals a. Very simple hack, and then we can use our root finding algorithms to find where some function equals any value, even if it's not 0. This is where it gets a little bit weird and unfortunately less sophisticated than we might like. Very often we're giving a function we know nothing about. And how do we at least roughly find these roots so that we can define bounds or make good guesses? And there really is not a clean, sophisticated method. It's experimenting with the function, plotting it, trying different ranges of x, or fixing the values of y and playing with it until you get a rough idea of where those roots are. Now, sometimes you might know something about the problem, something about the physics that helps you locate where those roots may be. Otherwise, it's just poking around at the command prompt in MATLAB until you can find roughly where those crossings are. And from those, you can identify your upper lower bounds or initial guesses to then feed into your root finding algorithm. Another thing that can change how you think about root finding. Suppose evaluating f of x for just a single value of x would take hours, days, or weeks. Let's just say it takes an hour. How would this change your mentality about how you approach a problem? And this very well could happen and happens in my research all the time, where we're running a simulation to evaluate some f of x. Maybe we're trying to calculate reflection from some device based on the dimension of something. That simulation could take hours, and in which case we're approaching these algorithms very differently. So I love this cartoon. There's two cavemen pulling a bunch of rocks, and they're using square wheels. So obviously they're doing a lot of work, and they're very busy because of that. And so they don't want to take time out to actually consider round wheels. And if you're only ever implementing these algorithms with functions that are very, very fast to calculate, because that's what happens in computational methods, we give you simple, easy things to solve, it doesn't put you in the right mentality. And what's the difference between an algorithm that converges in 10 iterations versus 20 iterations? That's huge if every time you evaluate f of x, it takes an hour. So think about this and consider that when you're really trying to minimize the number of iterations. Investigating some of these other types of root finding algorithms that can be a lot faster is definitely worth it. So our first method for root finding is called the bisection method. Let's jump right into that. So this is a bracketing method, and so we have some function, and we will define some lower bound and some upper bound that has to surround a zero crossing. If there is no zero crossing, this method could obviously fail, as you'll see. Also, if there's multiple crossings, this method will fail. So the assumption of the method is that we have nice bounds and that there is only one crossing between those bounds. Now we're plotting our function here. We may not always know this. We're plotting that function just for illustration purposes. So we know where the root crosses, but let's pretend we don't know that, and we'll implement this method to figure out where that root actually is. So after identifying where our bounds are and feeding that into the algorithm, the next thing we're going to do is make a guess as to where the root might be between those bounds. So being the bisection method, we choose the midpoint. So we calculate where the next root might be simply as the average of the position of the upper and lower bounds. Now that we've calculated where we think the next root might be, the next thing we do is evaluate the function at that new estimated position. So we evaluate the function at our new root position. At this point, we need to think about adjusting the bounds. And the way we'll do that is we'll look at the sign change from the bounds to where we've just evaluated our new root. So for example, in this slide, if we look at the function value at the lower bound and the upper bound, we see that there is a sign change. The fact that there's a sign change there means the root must fall somewhere between the lower bound and where we've just evaluated our function. Now, since we're drawing this big red line through here and we can see our function, it's obvious, but we won't always have that. But from the information of just that there's a sign change between the lower and upper bound tells us that the root falls between the lower and upper bound. So what we'll want to do is take the upper bound and move that to where our root is. So our root becomes our new upper bound. So that's exactly what we do. We move the upper bound to the midpoint. At this point, we sort of start over. We now have a new upper bound, the same lower bound, but essentially a new interval. And like before, we will calculate the midpoint because this is the bisection method. We calculate the new midpoint by averaging the positions of the upper and lower bounds. Since we have a new upper bound, our new guess as to where the root might be is now at this midpoint. Like before, now that we have our new guess as to the position of the root, we evaluate the function at that new position. Once we know this, now we try to consider the signs for the upper and lower bound to figure out on which side the root is. So we look at the sign of the lower bound, we see that it's negative, and we look at the sign of the function we just evaluated at our current guess. That is also negative. That means these have the same sign, and since they have the same sign, there can't be a zero crossing. This must mean that the root is between where our current guess is and the upper bound, somewhere in this interval. So that means we now need to move the lower bound up to the midpoint. And that's exactly what we do. And this process keeps repeating. We'll calculate a new midpoint. We will evaluate the function at the midpoint, check our signs, realize that the lower bound and where we just evaluated the root have the same sign. This must mean that the root crossing is between our current guess at the root and the upper bound. That means we have to move the we have to move the lower bound up to where our guess is at the root. And this process keeps repeating. Calculate the midpoint, evaluate the function, move the bounds. And this goes on and on and on until eventually we converge to where our root is. Something we have to think about is how we adjust our bounds, because the slope of the line can either be upward or downward. And if we are checking, for example, if both are negative, that's really not going to work. Or if both are positive, we need to just check that the lower bound and our current guess at the root have the same or different signs, whether that line is going upward or downward. So this changes a bit how we check for where the root is and how we adjust it. Let's talk more about that. So what we'll do is we will multiply the function evaluated at the lower limit with the function evaluated at our current guess at the root. If that product is negative, that means there's a sign change. And what's neat about doing it this way, that means there'll be a sign change whether or not that line is going upward or downward. And if there is a sign change, that has to mean that the root lies somewhere between the lower limit and our current guess. Therefore, the next step we should do is move the upper limit down to where the root is. And in the lower right of the screen, you can see the MATLAB code that does that. We're calculating this product, checking if it's less than 0. If it is, then that means there's a sign change and we have to move the upper limit. And we move the upper limit simply by copying XR over to XU and FR over to FU. Another thing that we need to realize about doing this is that does not require another evaluation of the function. We're simply copying information over. Now, if that function is very fast to calculate, this doesn't seem like such a big deal, but pretend for a second every time we call our function, it takes an hour to calculate. So just copying this information over eliminates the need for calling that function more times than necessary. Okay, so if the product is negative, we move the upper bound. Then we check that same product. If it is positive, that means that the function at the lower bound and the function at our guess at where the root is has the same sign. There is no zero crossing between them. That means the zero crossing must be between our current guess and the upper bound. So the operation then is to move the lower bound up to where we guess the root is. And in MATLAB, we see we do this with an else if statement. We're checking if it's positive, and we just copy the information over from our current guess at the root over to the lower limit. Now, a third thing could happen. That product could equal 0. This means we just got very lucky and we fell right on the root, in which case we're done. We don't have to iterate anymore. We found our root exactly. And this can happen sometimes. So how do we know if we're finished? One thing we should not do is to check the span between the upper and lower bounds. And it seems intuitive that maybe we should do this, and when those bounds close in, we know that we're finished. And that can work a lot of times. The problem is, sometimes depending on the shape of the function, it's always one bound that is moving. And if we're looking at the span between those bounds, the actual root might be pretty far away from the one bound that is not moving. And if we're checking the span, we'll never converge. So the proper way to do this is to check the difference between our new guess at the root and the old guess at the root. And when those changes become sufficiently small, we will end our algorithm. So here's a block diagram of the bisection method. So we will start, and we have knowledge of our function. Hopefully we'll also feed into it our upper and lower bound that spans one root. So really the first thing we do then is evaluate the function at the upper and lower bounds. Once we know that, we'll make our first guess as to where the root is, and that'll be the midpoint, simply by averaging the position of the upper and lower bounds. At this point, we enter into the main loop of the bisection method. And the first thing that happens inside that loop is evaluating the function at our new guess at the root. Once we do that, we then multiply the function value at the lower bound with the function value at our root, and we're checking the sign of that product. If it's less than 0, we know to move our upper bound, and we move that simply by copying information over. If that were positive, this product were positive, we move the lower bound. Either way, we've adjusted the bounds, and of course if that product is 0, we're done. But either way, we've adjusted our bounds, and now we calculate a new midpoint. Now that we have a new midpoint, we can check the difference between the old midpoint and the new midpoint and calculate this delta. When this delta falls below some tolerance, we can say that we're done. If it hasn't fallen below that tolerance, then we keep recalculating moving bounds, recalculating moving bounds, until the change in our guess at where the root is has fallen below some tolerance, and then we're done. This is simply a typed out version of the block diagram, maybe a little bit closer to computer code, but there's no information here that is not also in the block diagram. Some party notes on the bisection method. This is by far the most robust root finder. As long as we have two bounds that span a single crossing, this will find it. It will not fail. And that really can't be said about the other methods. The problem with it is that it's the least efficient root finder. It can take a while. And for fast functions that are fast to evaluate f of x, this isn't so much of an issue. But when the amount of time it takes to calculate f of x is minutes, hours, or even days, we want to try to minimize the number of iterations, and we have to use some more advanced algorithms. And usually what we give up in the more advanced algorithms, we have faster speed, but there's times where they can fail. Bisection method does not fail, but it tends to be the slowest. One thing that is pretty good to do is the last bullet in this list is maybe at the start of your code, rather than just jump into the bisection method, check the function value at the bounds, at the upper and lower limits. If they are the same sign, that means one of two things. It means there is no 0 crossing. That's bad. The method will obviously fail. The other thing that it can mean is that there's an even number of 0 crossings. So there's multiple roots within your bounds. And if you remember in the beginning, the assumption was that there really is only one crossing between the bounds, and we've chosen our bounds poorly. So think about doing that at the start of your codes, and if you do find that the sign is the same, error out of your algorithm. If you don't do that, you'll definitely come across some sort of error. It doesn't find a solution, or something else crazy happens, and it's harder to figure out what's happening. Whereas if you put this check in, you'll have a real simple error message telling you exactly what happened. Our next method is the false position method, and we can learn this very quickly because it is almost exactly like the bisection method. The only difference is in how we calculate the next guess at where the root will be. So we have the same starting point. We have a function, and we evaluate the function at the upper and lower bounds. If we were implementing the bisection method, we would calculate the position of the new root at the midpoint. However, the false position method fits this to a line, and it does a much more intelligent guess of where that root will be. Otherwise, the method's the same. It's just the equation we use to make our next guess as to the position of the root. So let's start over. We have an upper bound, a lower bound, the same function we were talking about, the bisection method, and we have the root that we want to find. Now we want to estimate a new position for our root. So what the method does is it essentially connects the point on our lower bound with the point at the upper bound with a straight line. And it figures out where that line crosses the zero. And that will be our new guess. And we can see that that actually is a better guess than choosing the midpoint, assuming that function is close to linear. For functions that are very nonlinear, that do a lot of curving, that may not be a better guess. Just like the bisection method, once we have our new guess, we evaluate the function at that new guess. And just like before, we adjust our bounds in the same way. We'll look at the sign change between the lower bound and our new guess. If there is no sign change, and there is not here, then that means we'll move our upper bound down. Otherwise, we move our lower bound up. So we move our lower bound up, and so on. And this works just like the bisection method, except we're always fitting to a line. So let's derive that new expression we have for estimating where the root is. And we start with the general expression of a line. So in this case, m is slope, and we also give it a point, some point x naught, y naught. Otherwise, that's the equation for a line. Given the function value at the limits, at the lower and upper bounds, we can estimate the slope of that line. Slope is just rise over run, and rise is the function value at the upper limit minus the function value at the lower limit, and the run, or the span in x, is just the difference between the upper and lower limits. So we know the slope of that line. Our equation for the line had a slope and one point. We can choose as that point the point on the lower bound. So if we plug in this value of x naught and y naught in our equation for the line, we end up here. And just to remind ourselves, this ugly expression here, that's the slope. So that's the equation for our line. Now to find out where that crosses zero, we set y equal to 0. So we set y equal to 0, and we solve this expression for x, and we interpret this as our new value for x. When we do that, we end up here, and we can use this equation to calculate where our new root position will be. It turns out we could have also used, instead of the lower limit for our point, we could have used the upper limit and derive a very similar equation. That's on the next slide. Same equation, we have the same slope, it's just that we put in a different point. In this case, we put in the point for our upper limit. It's the same line as on the previous slide, we've just used a different point along that same line. Now to find out where this line crosses 0, we set y equal to 0 and solve for x that we interpret as our new value of x. And we get a very similar looking equation. And it calculates the same exact point as on the previous slide. It's just using information from the upper limit instead of the lower limit. So we have these two equations that we just derived. Let's average them. So we average them by adding them together and dividing by 2. And we end up with this equation. Now this is an equation we want to look at in a little bit more detail and try to get some physical meaning of what's actually happening here. The first part of that equation is exactly what we did for the bisection method. But we had another term here, and we can interpret this as the correction term. This is what gives us a better estimate. And this full equation is the false position method. So the only difference between those two methods is this equation, and it's more specifically, it's that extra term. So we have a block diagram of this method. I won't step through it because it is exactly the same as with the bisection method. The only difference is when we calculate the position of our new root. We have this extra term here, and that is the only difference between false position method and bisection method. So what we can do is write one code. We can type in that big expression for calculating our new root, and then simply by commenting this off, we can convert our false position method to bisection method. We don't actually have to write two separate codes. We can just take that term in and out. Otherwise, it is the exact same method. We move our bounds the same way. We check for the magnitude of our change to see if we're done the same way. Everything's the same way. And for functions that are pretty linear between the upper and lower bounds, and that happens most of the time, this is an incredibly fast method, but it can fail or work really slowly when that function is not linear. Here's a picture taken out of our textbook, and in this case, the black line is the function we're trying to find the root of. And if we use the false position method, we are connecting the upper and lower bounds with a straight line. So our guess as to where the root would be would fall here and not even close to where the root actually is because the function is so nonlinear. So as we use an iterative algorithm to prove on that, it's only taking small steps to get to the final root. In this case, the bisection method would be much faster simply because this function is so nonlinear. Final notes, very similar to bisection method. In my mind, it is the same method, just a slightly different equation for calculating where the midpoint is. And most of the time when functions are linear, it converges much, much faster. But there's times where this can be slower, where it's very nonlinear. So if you somehow have knowledge that that function is very nonlinear between your bounds, you might want to use the bisection method instead of the false position method. Our last topic is multiple roots. Up to this point, we looked at our algorithms and assumed that there's only one root between the upper and lower bounds. Let's talk about when there's multiple roots. First of all, by looking at the function and its derivatives, we can make a pretty good guess as to whether a zero crossing represents a single root or a double root or something else. So for example, if we have a single root, and we're showing this here, we just see a nice well-behaved line crossing the x-axis. And if we look at the function value on either side of that point, we'll see a sign change. So we conclude if there's a sign change on either side of that point, and the slope is not zero, we definitely have a non-zero slope here, we have a line that's heading upward, we can conclude that that is probably a single root. Now in the case of a double root, this point that I'm circling here, that is a double root. Notice there is no sign change. The function goes up to that zero crossing, and it's not even really crossing. It just touches the x-axis and then comes back down again. So there is no sign change. So if there's no sign change, we can conclude it's a double root, or more generally, an even number of roots at that point. The slope is 0 if it's a double root. In fact, the slope is 0 if it's any multiple roots. And the curvature is the same on either side. The curvature, we look at the second derivative. So all of these are signs that we're actually looking at a double root, but it requires knowledge of the function and its derivatives. A triple root. We again see that we have a sign change on either side of the root. So a sign change really indicates that we have an odd number of roots. The slope is 0 at the point. That's very different than when we had a single root. The slope was not 0. So if we see a sign change and the slope is 0, we have a triple root. And the curvature changes sign on either side. That's also an indication we have a triple root. Quadruple root. This essentially follows all of the same rules as the double root, so it can be hard to tell the difference between a double and a quadruple root. But one thing, if we look at a quadruple root, is that the function stays flat over a longer span. It looks like it has very low curvature, stays flat. This was sort of a sharper point, if you will. And so visually, we can kind of tell the difference between a double and quadruple root, but it does become difficult. And by the time we talk about 5, 6, 7 roots, it becomes even more difficult. But most often, it's just single, double, and sometimes triple roots that we have to worry about. Well, we do have a problem when it comes to multiple roots and bracketing methods. Our bracketing methods required a sign change on either side of the root. That means if we have 2 roots, 4 roots, 6 roots, or really any even number of roots, we can't use our bracketing methods, at least not without modification. So we need a single or really odd multiple roots in order to use a bracketing method. But it turns out there's a very clever fix to this. We can define an auxiliary function u of x. And we can define this so that it has all the same roots as f, but it's guaranteed to always change sign on either side of the root. And that's really cool. So how we do this, we have our auxiliary function u of x. We define it as our original function f of x, and we divide f by its derivative. This auxiliary function has the same roots. How do we know it has the same roots? Because it has f in the numerator. But the interesting thing, if we look at the original f, for example, we have, let's go to this double root. There's no sign change here in f. We couldn't apply a bracketing method. But the red line is this auxiliary function, same root, but it changes sign. And hey, look, it's even pretty linear around that root. So instead of root finding on f of x, we simply root find on u of x, and we can use our bracketing methods. So this is just in words, the summary. We root find u of x instead of f of x.